Today we're going to start on section 1.2, which is on functions and graphs. So first of all, what's the definition of a function? So a function is a correspondence between a first set, which is called the domain of the function, and a second set, which is called the range, so that every element of the domain corresponds to exactly one element of the range. The intuitive idea behind a function is it's a rule. It's a rule that assigns every element of the domain exactly one element of the range. So you should think of the domain as the set of inputs and the range as the set of outputs. The function is what tells you which input corresponds with which output. We're going to represent a function in this class in several different ways. We'll start with arrow diagrams and sets of ordered pairs, and we'll move on from there to graphs and equations that define a function. Far and away the most common ways that we'll represent a function in this class are as graphs and equations. But for now we're going to start with arrow diagrams and sets of ordered pairs. More general than the concept of a function is the concept of a relation. So a relation is again a correspondence between a first set, the domain, and a second set, the range. But in this case, every element of the domain corresponds to at least one element of the range. So this is a little bit more general than a function in the sense that every function is a relation, but not all relations are functions. Let's take a look at some examples. In this example, we wanted to determine which of the following correspondences represent a function. So you'll notice here that both correspondences are represented with what's called an arrow diagram. So essentially the way that an arrow diagram works is it tells you which element of the domain, which in this case appears on the left-hand side, corresponds to which element of the range. So to tell which one is the domain, which set is the domain, and which set is the range, you just look for the tails of the arrow and the head of the arrow. The tails are coming from elements in the domain. The heads of the arrows point to elements of the range. So for instance, in this particular case, the element in the first column in part A is elements of the domain, whereas elements in the second column are elements of the range. So the question that we have to ask ourselves is, does this arrow diagram represent a function? Now remember that the definition of a function is a correspondence that assigns to every element of the domain exactly one element of the range. So in this particular case, 1 in the domain gets sent to 1 in the range. Minus 1, the element of the domain, is assigned to 1 in the range as well. 2 is an element of the domain which gets sent to 4, 0 gets sent to 0, and finally 5 gets sent to 25. Now you'll notice here that every element of the domain corresponds to precisely one element of the range. The key thing to look for in an arrow diagram is that no two arrows emanate from the same element of the domain. If that's the case, you have a function. So in this case, part A is an arrow diagram which is a function. Now at this point, go ahead and pause the video and determine whether the arrow diagram in part B represents a function. So in this particular case, the arrow diagram in part B does not represent a function. The reason that this is not a function is because the element 2, which is in the domain, corresponds to 3 elements of the range, namely A, B, and C. For that reason, 2 corresponds to more than one element of the range. Therefore, this arrow diagram does not represent a function. Next up, we're going to take a look at an example of functions represented as sets of ordered pairs. So the question wants to know which of the following are functions, and then once we've figured out which ones are functions, we want to find the domain and the range of those functions. So in part 1, we're looking at the set of ordered pairs 1, 0, 1, 2, and 2, 1. And in part 2, this set of ordered pairs, negative 5, 3, 5, 3, and 0, 3. So in each of these cases, you have sets of ordered pairs. Now the ordered pairs are coordinate pairs, x, comma, y. In all of the cases in this class, the x coordinates are going to be coming from the domain and the y coordinates are coming from the range. In part 2, the element -5 in the domain corresponds to the element 3 in the range. That is, the x value, the input is -5, corresponding to the y value, the output 3. In a similar way, 5 corresponds to 3 and 0 corresponds to 3. So let's take a look at which are functions and what is their corresponding domain and range. So recall from part 1 of this example that we're dealing with the set of ordered pairs 1, 0, 1, 2, and 2, 1. So in this case, the inputs are the x coordinates and the outputs are the y coordinates, and that's always how it's going to be in this class. So what this relation says is that the input 1 is assigned the output 0. That is what this first ordered pair says. On the other hand, the second ordered pair says that the input 1 is assigned to the output 2, and that's a problem. The input 1 is therefore assigned 2 different outputs. So what we have here is a relation, but we don't have a function. Now, in order to find the domain of a relation or a function represented as a set of ordered pairs, all you have to do is read off the x coordinates. Remember, the domain is the set of all inputs. So just like any other set, we denote this set with a curly braces, and then we just list off all the x values of the coordinates of all the points in the set of ordered pairs. In this case, 1, 1, and 2. And then we close the set up with another set of curly braces. Now you'll notice at this point that 1 shows up twice. Sets don't care about repetition and they don't care about order. So in order to write the domain of this set, it's just as well to write the set containing just 1 and 2. These sets are equal. In a similar way, the range is just the set of all y values. In this particular case, the range is the set containing the numbers 0, 2, and 1. Now at this point you want to pause the video and figure out whether the set of ordered pairs in part B represents a function. If it does, find its domain and its range. Go ahead and pause the video and come back when you figured this out. So in part B, this set of ordered pairs is a function. -5 is the input which corresponds to the output 3. 5 is an input which corresponds to the output 3 as well. That's all right. Nowhere in the definition of function does it say that no output can correspond to more than one input. So in this case, there's no repeated inputs in any of these ordered pairs with a different output. As a result, this is a function. Now once again, the domain is the set of all x coordinates of all points that appear in this function, which is the set of numbers -5, 5, and 0. As for the range, in this case the range is just the set containing 3. Notice here that I haven't bothered to write 3 times because sets don't care about repetition and they don't care about order. Now we're going to discuss function notation. So functions are important enough that they get their own notation. Function notation is written with the name of the function. So let's say you have a function f, followed by a parentheses, and then the input variable. Usually this is going to be an x, though not always. X's are common, t's are common as well. So the output associated with the input value x is written f of x. Another way to think about this is that f of x is the y value associated to the input x. The way that you read function notation is as follows. F parentheses x is read either f of x or sometimes f at x or the value of f at x. These latter two are a little bit, you'll hear a little bit less frequently. Probably 9 times out of 10 you'll hear this read f of x. So a quick note on the notation. F parentheses x does not mean f multiplied by x. It's an unfortunate reuse of the notation that can be very confusing the first time you see it, but it should be clear from context whether f of x means multiplication or function evaluation. This is one of the reasons that we have to be very careful about which letters we use for what. So for instance, x, y, and z almost universally represent variables, whereas the letters f, g, and h almost universally represent functions. This will help eliminate some of the confusion, and you'll sort of get used to it as we go, but it can be a little confusing at first because really f parentheses x is juxtaposition, which usually means multiplication. Here it means function evaluation. So let's take a look at how to use function notation in the following example. So in this case we have a function f. This function is a relation like any other. It's a rule that assigns an input to exactly one output, but this rule is being assigned via an equation as opposed to a set of ordered pairs, an arrow diagram, etc. So this particular function takes an input x, and the output that it assigns to that input x is 2x squared plus 1. So in this case we want to find f of 0, f of 5 times a, where a is just some variable, f of minus 1, and finally f of quantity a plus 5. So in this example we're given the function f of x equals 2x squared plus 1, and in part 1 we're asked to find the output corresponding to the input x equals 0. So the way that you'll hear most people refer to this is as plugging in the number 0 into the function. And what we literally mean when we say that is we're replacing all of the x values in the original definition of the function, in this case 2x squared plus 1, with the symbol 0. So I've made 0 in red here so that you can sort of keep track where we're plugging it in. So here what I've done is gone back to the original function, found all of the x's, and literally replaced the symbol x with the symbol 0 in parentheses. These parentheses are sometimes necessary, but believe me, you will thank yourself when you avoid a lot of problems later on because you've gotten into the habit of always plugging things in parentheses when you're doing function evaluation. Get into that habit, you'll thank yourself for it later. So 0 is in parentheses here. So what we end up with is 2 times 0 squared, which is 0, plus 1, which equals 1. So what this tells us is that f of 0 is 1. Another way to say that is that the output corresponding to the input x equals 0 is y equals 1. For part 2, we're going to plug the quantity 5a into the function f. In other words, we're going to find the output corresponding to the input x equals 5a. Once again, we're going to go back to the original definition of the function, find everywhere that an x appears, and replace it this time with the string of symbols 5a, always in parentheses. So you'll notice here that I've replaced the symbol x with the symbols in red this time, 5a all in parentheses. Now all we have to do is simplify our result by combining like terms if there are any. You'll notice the square applies to the entire quantity parentheses 5a. When we square 5a, we get 25a squared, which when multiplied by 2 gives us 50a squared plus 1 in the end. This is about as simple as we can get in this particular case because there are no like terms to combine. So what this tells us is that the input x equals 5a corresponds to the output, or the y value, 50a squared plus 1. Now at this point you want to go ahead and stop the video and evaluate on your own f of minus 1 and f of quantity a plus 5. When you're done, go ahead and start the video from here. So in part 3 of this example, we plug negative 1 in for x, which I've written in red here. So we end up with, instead of 2x squared plus 1, 2 times quantity negative 1 quantity squared plus 1. Negative 1 times itself, that is to say negative 1 squared, is 1. Times 2 is 2, and plus 1 in the end is 3. So 3 is the output corresponding to the input x equals -1. Now, for part 4, we're plugging in the entire quantity a plus 5 in for x. And once again, I've been careful to plug it in inside parentheses. So what we end up with is 2 times the quantity a plus 5, quantity squared, plus 1. Now you'll notice here that a plus 5 quantity squared is not a squared plus 25. Though this is a very common mistake in a problem like this. Instead, we have to FOIL out a plus 5 times the quantity a plus 5. And what we end up with when we do that FOILing is 2. This 2 here is the same as this 2 here. A plus 5 quantity squared is a squared plus 10a plus 25. This plus 1 out here is the same as this plus 1 here. Now, we distribute that 2 and combine like terms. And what you should end up with, once you've done that distribution, is 2a squared plus 20a plus 51. This quantity here is the answer. That is, 2a squared plus 20a plus 51 is the output corresponding to the input a plus 5. Next up, we're going to work our way through the following example. We want to graph two functions here. F of x equals x cubed minus x, and g of x equals root x plus 1. Now, in the end, we only have some very primitive tools to graph these functions, namely finding some x values and their corresponding y values. And in the end, we would do this with a t-chart, but that gets really tedious after a while. So instead, we're going to use our calculators to graph, to find a few ordered pairs, the x coordinates and their corresponding y coordinates for these two functions. So you'll notice here that I've got my TI-83, your TI-84 will work in pretty much the same way. Now if I go into the y equals menu, I'm going to enter this first function, f of x equals x cubed minus x. Now to enter a cube here, you use this little caret button over on the right hand side. That's x to the third power minus x. Now in this case, I want to come up with a set of ordered pairs, x coordinates and their corresponding y coordinates. And to do that, I'm going to use my table. So if you hit the second button and then the graph button, which brings you into the table, you'll see a bunch of x values and their corresponding y values possibly. Now, you won't have to reset your table set every time you use the calculator. If you haven't done this already from the first video, you can do it now. You enter the table set menu, go to the independent variable and set it to ask, and then go back to your table and it should either be blank or with a few values that you had in there from the first video. So I'm going to choose a few different x values here. Let's do minus 3. Ooh. So you should know that there's a difference in syntax here. That's a subtraction. We need a minus. So that should be minus 3, minus 2, minus 1, 0, 1, 2, and 3. Now at this point we could continue on in this manner, finding x values and their corresponding y values. So notice what your calculator is doing here. In that first row, for instance, it's taking the x value -3 and plugging it into the function. It turns out that the corresponding y value is y equals minus 24. Now the nice thing about using your table is you don't have to plug these things in at this point. You can just tell your calculator to find the y value associated to the x value, x equals -3, and it'll do it for you. The bad news is if there's any variables involved here like an a or an m or whatever, your calculator won't do symbolic computation like that. So this only works for numbers. Now we could graph all of these points and try to draw a smooth curve in between them, but we don't have enough information at this point to determine whether or not we have enough points to reliably graph this function. So instead, I'm going to hit the graph button and take a look at what this graph looks like. Now you'll notice here that I have a lot of blank space over on the sides of my calculator here. I'm seeing the graph, of course, and we think that it's everything that's significant about this graph, though we don't really know. But I want to try to fill up some of this empty space. Each one of these tick marks right now is set at 1 unit, and we go from -10 in the x direction to 10 in the x direction, -10 in the y direction to 10 in the y direction. I want to narrow that up a little bit. And it looks to me like the x values go from about x equals -3 to about x equals 3 here. So to adjust the view that I'm seeing here, this rectangular region that you're looking at the graph through is called the window. And to adjust that window, you press the window button. X min is the lowest x value that appears, and x max is the highest x value that appears. Now, I'm going to change the x min to -3 because that's about where the graph was ending according to the y values that we had chosen. And my x max I'm going to set equal to 3 here. Now you'll notice this XSCL, that's x scale. It's the distance between the tick marks on the x-axis here. So I have it currently set to 3. I'm going to go ahead and set it to 1/2, so to 0.5 units, and I'll show you how this affects the graph. So when we go back to the graph, what you should see is something that looks like the following. Now, notice how this graph gets closer to the edges now. Also, the tick marks are at every half of a unit. So the distance between this tick mark here and this tick mark here is half a unit. As a result, the distance between this tick mark and this tick mark is now 1 unit. You can change that by changing the x scale variable. Now you'll notice here that it looks like I got a bump here and a bump here, but I'm not really seeing it. So I want to shorten up my y values a little bit. I think I'm not going to go above maybe y equals 1 or maybe 2 tops. So I'm going to go back into my window and change my y min to -2 and my y max to 2. So I'm going to go from -2 in the in the y direction to 2 in the y direction. Now, adjusting your window is some trial and error, and the more you practice this, the better you'll get at sort of guessing what's a good window to use. So I definitely encourage you to play around with this a little bit. So if I go back to the graph here, now I'm seeing a really nice picture of what this graph looks like. And you'll notice that I can actually read off the x-intercepts. The x-intercepts are at -1. Notice that's 2 tick marks because my x scale is to 1/2. So my x-intercepts are at -1, the origin at 0, 0, and at 2, 0 over here. Now, if you want to set the window back to its standard without having to go through and type in all of the numbers, if you go into the zoom menu here, it's going to look like this, and you want to select Z standard, which you can do either by scrolling down with your arrow keys or just by hitting the number 6. And this will reset everything to the -10 to 10 window. So that being said, go ahead and pause the video at this point and try to graph g of x, which is root x plus 1 on your calculator. So let's go through the solution of this. Now, I could delete x cubed minus x from my y equals menu, and it's fine if you did that, but I want to show you another trick to deal with on this. I'm going to type in g of x in the second y variable here, into y2. So that's the square root, which is right above the x squared key, of x plus 1. Now, you don't have to close the parentheses off here, but I will. You can get away without it in this case. Now, if you hit the graph button, you're not only going to see the graph that you had from before, that is f of x, but you're also going to see the new graph g of x, which I don't want. So I'm going to go back into my y equals menu, and I'm going to use my arrow keys to scroll over to this equal sign, and you'll notice that it's highlighted. So if you highlight that and you hit enter, now it's unhighlighted, and if I go back to my graph, I'm no longer going to see f of x, just g of x, which is the only thing that's still highlighted. So once again, I'm going to adjust my window a little bit. At this point, pause your video, make sure that your window is adjusted. Come back and then you can see how I adjusted mine. So at this point, it looks like my lowest x value is at about x equals minus 1. On the other hand, my highest highest y value is no higher than 3, maybe 4. So I'm going to go into my window. I'm going to set the x min at negative, let's say 3. See how that looks. X max I can leave at 10. Y min I'm going to set to 0 and y max to 4, and then take a look at the graph. It's a much nicer looking graph. It's utilizing a lot more of my calculator's sort of window looking into this graph. So what we're going to talk about next is called implied domain. So when a function f of x is given by an equation, the domain of f of x is assumed to be the set of all real number inputs which give a real number output when plugged into f of x. That is, if you take an x value and plug it in, you should get a real number out. If it's not a real number, that x value is not in the domain. This is sometimes called implied domain because nobody ever says what the domain is. It's implicit. When an input results in an expression that is not defined or is not a real number, we say that the function value does not exist and that the number being substituted is not in the domain of the function f of x. This all sounds very complicated, and the truth is it can be. For that reason, this subject gives a lot of people trouble all the way through this class and through the next few classes as well. So what I want you to take away from this is the following tip. Whenever you are asked for the domain of a function given in terms of an equation, here's what you should be looking for. 2 things and only 2 things. The first is divide by 0 problems. You can never divide by 0 and get a real number. It's undefined. The second problem that you want to look for is a negative under an even root. Remember, that's square roots, 4th roots, 6th roots, 8th roots, etc. Anything with an even index. These are the 2 problems that you always want to look for. When you get rid of these problems, what you're left with is the domain. And by getting rid of the problems, I mean taking the set of all real numbers and removing the problems. This will become a little bit more clear in the next example. This list is complete for most of this semester. At the very end of the semester, when we talk about logarithms, we're going to add one more thing to this list. 3 problems: divide by 0, negative under an even root, and one more that we'll see later, and that will take you through all the classes you'll ever have to take, unless maybe you're a math major, in which case you may have to add a few more onto the end of that list. So let's take a look at an example. So in this example, we're given 3 functions in part 1, 2, and 3 respectively. We want to find the domain of each, and we want to express our answer in both set builder and interval notation. In the first part of this example, we're asked to find the domain of the function f of x equals 1 over x plus 2. So if you go back and consult that list that we just talked about, we're looking for divide by 0 problems and negative under an even root problem. Now there are no square roots or 4th roots or anything like that in this example, but there is the possibility of a divide by 0 problem. Here's how you find it. We're going to take the denominator, which in this case is x plus 2, that is the thing that we're dividing by, and we're going to set it equal to 0. Solve the resulting equation. You'll get x equals minus 2. Now, I'm going to do some scratch work over here on the right-hand side because I want to demonstrate what we've just figured out. If I was to take negative 2 and plug it into this function, let's see what happens. So I'm going to take negative 2 and I'm going to plug it into this function. What we will end up with is 1 over, now I'm substituting negative 2, always in parentheses, in for the symbol x, and then the rest of the denominator is plus 2. Now, when you simplify the denominator, you get 0, and that's a problem because we get 1 divided by 0. This quantity here is undefined. It simply does not have meaning. So imagine the following. You had a room full of monkeys. They're all hammering on typewriters. Most of the time, they're going to be writing nonsense. It's meaningless. It's undefined. 1 divided by 0 is the mathematical equivalent of that situation. It is simply left without meaning. As a result, -2 is not in the domain of f. That is to say, -2 is a divide by 0 problem. Now, we're going to write down our domain of f in this case, first using set builder notation. The set builder notation in this case looks as follows. So on the left-hand side of this equation, I've written dom f. That's short for domain of f. It's kind of a play on function notation here. And on the right side, we have a set which is surrounded in curly braces as usual. So the way that this set is read is the set of all x such that x does not equal -2. So strictly speaking, this open curly brace here is read the set of all. This vertical line is read such that. So putting this all together, this is read the set of all x such that x does not equal -2. Now you'll notice what happened here. When we solved this equation, we had an equality here. That changed to an inequality at this point. When I say get rid of the divide by 0 problem, this is what I mean. At this point, we found the divide by 0 problem. And then we got rid of it here. We got rid of it by removing it from the set of all real numbers. In the end, the domain is the set of all x such that x does not equal -2. Another way to say this is any real number is in the domain of f except -2. Everything else works. Now, this question has also asked us to write our answer in interval notation. And the easiest way to translate from set builder notation to interval notation is with a picture. The picture that I'm going to use here, I'm going to make some scratch work down at this point. It's a number line. And the only number of interest that I have on this number line is the divide by 0 problem that we found before. And that's at -2. So I'm going to go ahead and label that on my number line. Now, depending on the book that you used in the previous class, you may have used an open circle or a closed circle on this number line. In our particular book, we use a parentheses here. Parentheses on both sides essentially eliminates -2 from the number line in this case. So I'm going to go back here and I'm going to shade in all of the values to the left of 2 and all of the values to the right of 2. And now, in order to come up with my interval notation, I'm going to start from the left-hand side of this number line and move towards the right-hand side. You'll notice that everything to the left of -2 is shaded in. That interval goes all the way back, and the way that we represent that is in interval notation with a -infinity here. Now you'll notice the parentheses that I just wrote right here. Those parentheses mean don't include this number or symbol. So in this case, -infinity and +infinity always get parentheses, never brackets, because -infinity is not a real number. So we keep marching from left to right on our number line until we hit the first parentheses or bracket that we have written. And that's at -2 in this case. Now, -2 is not included because of these parentheses. As a result, we're going to put parentheses on our first interval. You'll notice that the parentheses on our interval correspond to the parentheses on the number line. And then we continue our march from left to right, starting at -2, going all the way to the right going to infinity. Once again, always parentheses on infinity. In between these two intervals, we put a union, which means anything in the first set or the second set. So what we have here is the domain either written in interval notation, in set builder notation or interval notation. Now at this point of the video, you want to pause it, work on parts 2 and 3, find the domain in both set builder and interval notation, and then come back to see my solution. So for part 2 of this example, we're dealing with the function g of x equals x plus 2 over quantity x squared minus 4. Now, the two things that we're always looking for when we're finding domain is divide by zero problems and negative under an even root. There are no even roots here, so the only thing that we have to concern ourselves with is a divide by zero problem. This occurs exactly where the denominator is 0. That is where x squared minus 4 equals 0. So if we factor the left-hand side in this step, we get x minus 2 times x plus 2 is 0. That's by difference of squares. The zero factor property says that as a result, x is either 2 or negative 2, and those correspond to the first and second parentheses respectively. So what we have is when x is 2 and when x is negative 2, we get divide by zero problems. Now we're going to write our domain in set builder notation. So when we do that, what we get is that the domain of G is the set of all x such that x is not equal to and negative 2. So you'll notice here that we found the divide by zero problems at this step. And at this step, we got rid of them. That is, we took them out of the set of all real numbers. Now, in order to translate to interval notation, we're once again going to use our number line. In this case, we have two values of interest. X equals negative 2 and x equals 2. We want to rule out these numbers, so we put parentheses at each of them. Everything else gets colored in. And once again, to find our interval notation, we march from left to right. So our first interval goes from minus infinity to minus 2. Our next interval goes from minus 2 to 2. And finally, our last interval, which I'm going to write down here on the next line because I ran out of space, goes from 2 to infinity. Parentheses on every end of each of these three intervals. So for part 3, we're looking at the polynomial function h of x equals x squared plus 2x plus 2. Remember, when you're looking for domain, you're always looking for two problems. Divide by zero problems and negative under an even root problem. Notice there is no division in this function, and as a result, there can be no divide by zero problems. Furthermore, there are no roots in this problem, so there can be no negative under an even root problem. As a result, the domain is the set of all real numbers. In set notation, this is written the set of all x such that x is just any real number. Now in interval notation, there's nothing to pull out of the real number line. So what we get is the interval from minus infinity all the way up to infinity. Now this is the set builder and interval notation respectively, but there's another notation that you'll often see used when the domain is the set of all real numbers. That notation is this, what's called blackboard bold R. So the way to make this blackboard bold R is to make two lines and then finish it off by making an R across both lines at the top. So this guy here is shorthand for the set of all real numbers. So now we're going to do one more example that involves determining whether a graph represents a function. So in this example, we're given a few different relations and being and are asked to determine which of these are functions. So in part A, we're given a graph. It's the red curve here, and we're asked to determine whether this graph represents a function. So the easiest way to determine if a graph represents the function is to apply what's called the vertical line test. And the way the vertical line test works is as follows. So imagine we have a green vertical line that looks like this. And imagine this line sweeps horizontally across the picture. Now, the question that we want to ask ourselves is, as this line sweeps from left to right, does it intersect the graph in more than one place at any given time? If the answer is yes, the graph fails the vertical line test and does not represent a function. So in this particular case, this graph does not represent a function because, for instance, this green vertical line intersects the graph in 3 places. Essentially what this means is there's a single x value, wherever this green vertical line happens to be, that corresponds to 3 different y values, which is not allowed in the definition of a function. So this graph does not represent a function, the reason being it fails the vertical line test, which I'll abbreviate VLT. So at this point, go ahead and pause the video and see if you can determine whether the graph in part B represents a function and the equation in part C represents a function. So the graph in part B does represent a function because it passes the vertical line test. Now, on the other hand, part C is an equation. We don't have a graph to work with. But one thing that you'll notice in this case is that both 0, 1 and 0, -1 lie on the graph. That is, the input x equals 0 corresponds to 2 distinct outputs, y equals 1 and y equals -1. As a result, by definition, this equation is not a function. So that concludes the lecture for section 1.2 on functions and graphs.